All right. Our, I think we're live. I think we are live. Okay. Please comment if you can hear me, if you can see me. So sorry about yesterday. It's terrible. Really terrible with this technology. Even now, it took like a minute to get everything up and running. Um, I'm going to be sending this link now to everyone. So please be patient. Oh, gosh. Can we please comment if you can hear me? I hope you can. It's coming. It is coming. Oh my God. Okay, we are live. And then the whiteboard is coming to that link. Can you hear me? We should be live. So just let me know if you can hear me. Are we there? And good morning. I hope you are there. It says that I'm live. Oh, great. Awesome. 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 Okay. So we'll just wait for a few more hellos. And again, so sorry about yesterday. Hi, Sarah. I'm glad that you can hear. Again, I'm not too sure how long of this delay is happening right now, but we're going to work with what we have. Okay. So if you have any questions from the homework, we can look at that now. I think this is what I wanted to cover. I'm just going through here. The remainder theorem. I think that's what I wanted to look at yesterday. No, we already looked at that. No, potential zeros, excuse me. Right. So if you had, let me look here. Was this the homework? No, this we already looked at. I'm so sorry. The zeros of a the factor theorem. That's it. Good morning, Dahlia. Good morning, Josh. Good morning, Gianni. I hope there are a few more of you that chime in. So this is what I wanted to accomplish yesterday. The whiteboard should be up and running. So let's just test that quickly. Um, so please tell me if that if that came up. Now I'm testing the whiteboard. Hi, Leah. Hi, Mahmoudal. Hi, Cindy. Can someone just write what I wrote on the board? I just want to make sure that it's working and that you see it. So again, I just wrote something on our whiteboard and I just want to make sure that you can see it on your end. That's right, Josh. No tech, no good. All right. So let's work with the tech that we do have. Let me just erase that. So the board is up and right. Thank you, Leanna. So again, sorry about yesterday. I hope everyone had a good Monday. We're now Tuesday. And let's get the show on the road. So any questions from what I shared with you yesterday? Essentially, what we're going to be looking at today for the most part is just making sure that you understood what we should have covered yesterday, and I'll continue on with the chapter. So are there any questions from the material that we were supposed to cover yesterday? So basically what we're looking at now is the factor theorem. And we kind of hinted at that on Friday, believe it or not. So if there's any part of the homework that you want to go over, I believe I assigned 1A, 1B, 1C, and number 2. But if there's something from there that you want to look at specifically, I'll take the time. Question 2 from the homework. So let's look at that. I'm going to pull it up on my end. So let's look. Hold up. So I hope we're talking about the same question here. Let's see. Factor, yes, to factor f of x into linear factors. So in other words, so you're given a k value. So let's look at this. This is actually good review. So we have f of x. So here, now on my whiteboard, so we have f of x, and that's going to equal to 5x cubed plus 4x squared minus 11x plus 2. So basically, if our k value is negative 2, I need to know what we're dividing this by. So again, if k is negative 2, what are we dividing this whole thing by? 3 we're going to look at today, Kyle. So I only assigned for homework 1A, 1B, 1C, and number 2. Like, you're free to answer or try questions like 3A and B, but that's going to be our conversation for today. And I think I appeared in the live stream for a second. All right, so what are we dividing this by? So we're looking at the whiteboard. I just want to make sure that we know what k equals negative 2 means. So if someone can just chime in and essentially give us the denominator here. So we're looking at the whiteboard. Again, the whiteboard link was shared. It's in our Google Classroom. So I want to make sure that we know what we have to divide this polynomial by. All right, so that could be part of the problem, I suppose. So can you still hear me? I'm just curious. Thank you, Leah. Exactly. So if I'm just going to cross this out for a second. And we have here, it is still f of x, but we're dividing that entire polynomial by x plus 2. But if we perform the synthetic division, so again, this is still good practice with the synthetic division. I'm moving down this way so we can set up the synthetic division. So we have negative 2, and we're going to be dividing that into the following. So we divide that into the coefficients, 5, 4, negative 11, and here we have positive 2. So if we do this, so just again, quick review, scrolling down here, we should have 5, this becomes negative 10, or this becomes negative 6, this becomes positive 12, so use this with 1, negative 2, this is 0. So once we have this, I'm just scrolling down, so hopefully you found something like this. So then here we have 5x squared minus 6x plus 1. So any questions so far with that? So this is the division now, but it doesn't answer the question. So the question here is not answered, because what they want us to do is this. So here, I'm just scrolling down. So please follow along. So basically, when we have the polynomial 5x squared, cubed. So we're starting from the beginning, what we were given. 5x cubed plus 4x squared minus 11x plus 2. All of this is going to equal 2. So I'm going to just highlight what we found. So this piece, right, 5x squared minus 6x plus 1, but I'm going to move in this direction now a little bit. It has to be multiplied with x plus 2. So do you follow along with what I just did there? So are there any questions up to this point? We're still looking at question number 2. I believe this is 2A that I'm looking at. Focusing on 2A. Any questions so far up to what just happened here? So are we okay with what you're seeing here? So I'm just moving again. So basically the question is asking us this. So I'm moving along in the whiteboard. The question now, no questions. Okay, so if we look here, this piece, what I'm circling in purple, I have to factor this. That purple factor, the trinomial, it has to now be factored. So we already have x plus 2. That's one factor. So now this has to be factored, but we have to perform the AC method of factoring. So in other words, if you remember, we have values of a, which in this case are 5, b is negative 6, and c is 1. So if we use a times c, it gives us 5. But the factors of 5 that add to give us negative 6, it has to be negative 5 and negative 1. So I'm moving down this way. So please follow along. So here I'm just rewriting. So the factors, so this is what, 5x squared. So I'm going to write minus 5x minus 1x. And what was it, plus 1? Right. So this has to be now factored by grouping. So we're kind of reviewing what we did before. And if we have that, we have 5x times x minus 1. And I factor a negative 1, and we're left with x minus 1. So this is kind of more tedious and it's more applied because not only do you have to divide, right? So applying the synthetic division, but then once you have your quotient, you need to see if that's factorable or if you can do something like this. So when this is all done, you have 5x minus 1 times x minus 1. But that's still not the final answer. So moving down, just scrolling, and I'm moving down. We have this. This is going to be the final answer because when you divide it, I know it's going to be a little bit overwhelming. So when you divide it, 5x cubed plus 4x squared minus 11x plus 2. When we divided that with x plus 2, we said that x plus 2 was a factor. Now we have two additional factors. We have 5x minus 1 and we have x minus 1. So basically, when you do everything here, if you multiply, you will get this. Does that answer the question, or what you essentially had to do with question number 2? So to say it in English, the instructions for what you needed to do for question 2. Divide using synthetic division, and then factor further if necessary. That's what you had to do. Divide with synthetic division and factor further if necessary. Any questions so far? Or any additional questions? And just so you know, I'll be sharing the solutions to this towards at some point today, probably immediately following this class. So this way you have them to review. So any other questions? Maybe yes, maybe no. I hope everyone's sleeping a little bit more now that we have some flexibility with time. And I hope everyone is doing well and is safe and healthy. I take the silence as a no, and I'm actually afraid to do anything on my computer that's streaming because it's just so slow. Do we have to multiply all of them at the end? Great question, and thank you, Eleni, for asking. So I'm going to highlight the question, the answer to the question. This is what the question is asking. What I just boxed in red. So it's saying factor f of x into linear factors given that k is a 0. So basically, when they're telling you that k is a 0, you're not going to have a remainder. So when you do end up dividing, you're going to be left with a trinomial that in these examples, that the ones that I'm giving you, the trinomial will be factorable. So that's basically what we did before. We divided x plus 2 into the polynomial. We got 5x squared minus 6x plus 1, and then we ended up factoring that into 5x minus 1 times x minus 1. So basically what I just boxed, that is the answer. And what I said there, multiply, if you were to go through the whole process of multiplying those three factors together, it could get a little bit messy. You will end up with what you started with. That's why I wrote wow. I hope that's clear. All right, so we're going to move along so we can make the most of the time that we have left, because you guys are really good at reminding me when this class is over. I don't want to name names. All right, so we did the factor theorem. This is basically what we just went over, and I gave you everything in the slides that was shared. Right, so this is kind of, if you can see, let me see if this is projected right now. Yeah, there's a delay. At some point, the slide will change. Or what's in front of you, there we go. It's a little slow. So basically, this slide is showing you what we just did. So once you divide, you're probably going to be left with the trinomial. Factor that further, and that ends up being the answer. So moving along, let's see what we have. So this all is going to lead to what's called the fundamental theorem of algebra. So let me make sure that you have that in front of you. All right, so, and again, I apologize for the delay. So, fundamental theorem of algebra. Every function defined by a polynomial of degree 1 or more has at least one complex zero. So it's kind of confusing. So I'm going to just go through this slide. So the fundamental theorem of algebra establishes that the number of roots, so another way to think about this, if you were to graph this, if you were to go into Desmos and plug these functions in, they may look a little odd depending on the degree of the polynomial, but when you graph it, maybe I can zoom in on this. Yeah, I think it will work. I hope. Hopefully it doesn't look too distorted. So basically, we're looking at roots, or the zeros, where the graph will intersect the x-axis. So in other words, according to this theorem, according to this theorem, the fundamental theorem of algebra establishes that the number of roots and the type of roots for the polynomials. So a function defined by a polynomial of degree n has at most n distinct zeros, and that we already spoke about. But like that's what happens when we do a lot of the stuff in this class or in math in general. We end up, I don't want to say taking things for granted, but some things are kind of assumed, or like duh. But we have to move away from sometimes what's logical and apply appropriate vocabulary. So that's what one of these things, or this specific theorem, is trying to do. So basically, if you remember when we did x squared, or a quadratic equation, we would typically have two roots, or two zeros. If we have x cubed, we would have three roots, or three zeros. Or if the graph was plotted, you would see that it would intersect the x-axis 3 times. Similarly, x to the fourth, you would have 4. And if you even go back to what we just what we just factored, the 5x cubed plus 4x squared minus 11x plus 2, that homework example. You had 3 factors, you set them all equal to 0, you will get 3 values of x. So that's basically what this rule is saying. So again, a function defined by a polynomial of degree n has at most n distinct zeros. Number of zeros theorem. Also, functions with complex roots must be in conjugate pairs. A plus bi and a minus bi. So that can kind of be a little bit confusing. So moving along here. So let's look. So you should have example 1. Let me see if I can get rid of this. All right, so you should have your classwork. And we're looking at the following. So some of the conditions here. So it says here, find a function f defined by a polynomial of degree 3 that satisfies the given conditions. So this is where this gets a little bit complicated. Right, so our zeros are going to be -1, 2, and 4. And then when we evaluate the function, when it's 1, or when f of x and this x value is 1, it's going to equal to 3. And it's okay if you're confused right now. It's okay. So what we want to do is we want to take all of this, basically these conditions, and write a function. Or have something where f of x equals 2. So if you look in the previous slide here, so I kind of rushed, or not rushed, but I went into the example so that I can refer back to this piece here. So this looks very complicated. I don't want to get into all of the specifics, but we're going to follow the formula where it says f of x is equal to some constant a, and we're going to be multiplying that constant a with these factors that make up that function. So basically where I'm highlighting this, that's going to be a guide that we're going to use in order to take some conditions, like specific zeros, and when we evaluate a function and we get an answer, all of that's going to be used to essentially create a function. Now I will say this in English. We're going to be given information, and we're going to use that information to create some type of polynomial. That's basically what we're doing. And we're going to be following this rule, or this theorem called linear factorization theorem. So if we look here, we have zeros of -1, 2, 4, and we have the evaluation of the function. When it's f of 1, it'll give us 3. So, first thing, so let's go to the whiteboard. Oops. So if we go to the whiteboard, I'm moving down now. Moving down. So we're at the whiteboard. I'm drawing all of these arrows as we're moving down. So here's some zeros. So if we think about it, x will equal to -1. X will equal to 2. X will equal to 4. But it was really, before x was by itself, it equaled to 0. It equaled to 0. It equaled to 0. What equaled to 0? So if it was -1, it was really x plus 1. If it's x equals 2, it was really x minus 2. If it was x equals 4, it was really x minus 4. Oops. So I hope you're looking at the whiteboard right now. Because essentially what you're doing is you're getting the right-hand side to equal to 0. So what ends up happening is that these zeros are really factors. So you end up with x plus 1. You end up with x minus 2, excuse me. And x minus 4, you're multiplying all of that together. But what you need to do now is you need to find a coefficient, because it's not assumed that this is the answer to the polynomial where when you evaluate it, for f of 1 that you get 3. So what we need to do is this. So basically this is what we did right now. So this is repeating what I just did on the whiteboard. It's now just in front of you. So since f of x is to be of degree 3, right? There are only 3 zeros here. So these are the only possible factors by the number of zeros theorem. Therefore, f of x has the form f of x is equal to all of this. So I can put it here that this is equal to f of x, but what we don't know is what's called the leading coefficient. So I'm going to put an a in front here. Are there any questions so far before I continue? I know this is kind of overwhelming, but it's an extension of what we've been doing. So I'm going to take a pause here for maybe like 5-10 seconds. If you have any questions, please let me know. Oh, let's see. Some feedback. Let's see. What if you are only given 1 0? I mean, you could, then we would follow the same process. So if we only had -1, then f of x would then be equal to a times x plus 1 as an example. But then we're looking at a linear equation at that point, because then we have degree 1, if that makes sense. Right now we have degree 3, which means that when we multiply these factors together, so x plus 1, x minus 2, x minus 4, if you think about it, it's x times x times x, or x cubed, which that then makes the polynomial degree 3, or the variable that's there, the highest power of that specific variable is 3. Does that make sense? So let's move along. So now what we have to do is we have to solve for a. But there's guidance here. You're told how to solve for a. You're told that if you substitute a, or x, excuse me, for 1, that you should get 3. So in other words, what we're going to do is the following. So we're going back to my whiteboard. I'm just scrolling down. And what we're going to do is we're going to evaluate now. When f of x, or in this case x is 1, I'm just going to write this. So f of 1. We still don't know what a is, but we know that x is 1, so I write 1 plus 1, 1 minus 2, 1 minus 4. But here's the thing. Wait, hold on. Question here. So, hold on. So how would you answer 3b? Are we going to touch on that topic? Oh, I'm getting there. If we're talking about the classwork, we're getting there. So degree 4 would be x to the 4th power, right? Or some variable raised to the power of 4. Correct, Kyle. So when we solve here for a, remember f of 1, I'm going back to the whiteboard. F of 1 is really 3. And we know that 1 plus 1 is 2. 1 minus 2 is -1. And we have here -3 for 1 minus 4. So I'm still on the whiteboard, and if we multiply all of this, we should have the following. We should have, let's look. We have 6a equals 3, or a will equal to 1/2. because when you divide 6 to both sides, you're left with 3/6, or a equals to 1/2. Or basically it's here. If you want to take a look, this is exactly what we just did. So a equals 1/2. So when you go and now try to write this function where you have the zeros of -1, 2, and 4, and when you evaluate that function for 1, or when x equals 1, and for it to give you 3, the a value, or the constant, or what's called the leading coefficient, should be 1/2. So if we put it all together, we would have the following. This will be the final answer. So find a function. These are equivalent ways to write this. So you could leave it as f of x equals to 1/2 times x plus 1 times x minus 2 times x minus 4. You could leave it that way. Or you can multiply everything out. I think a lot of you would vote or would opt or would choose the top one or this one. Much easier. I mean, if you want to challenge yourself, feel free to multiply everything out. But note the a value and how that's going to be the leading coefficient here for that x cubed term. So now this is what Valentina was asking about letter B. So it's the same idea. So if we move now to letter B. So it's saying here, find a function f defined by a polynomial of degree 3 that satisfies the given conditions. This multiplicity. This is what is kind of bothersome. Because here's the reality. So let's look here. So I'm at the whiteboard. I'm going to do this quick because I know we don't have too much time. So if we look here. So if you think about it, let's say I have x squared plus 4x plus 4. If I factor this, this should be x plus 2 times x plus 2. Oh, we're looking at that example. Let me choose a different example. Sorry. So if I have x squared plus 6x plus 9. If I factor this, this becomes x plus 3 times x plus 3. But if I solve this for 0, I will have -3 appear 2 times. But it's only one solution. So although we say x equals -3 in the example that I have on the whiteboard, it's appearing twice, or it has a multiplicity of 2 in this case, because it's appearing 2 times. So if you look at this example, it's saying that -2 is a 0 of multiplicity 3. So in other words, that means, so I'm going back to the whiteboard, and the solution is in front of you also, but I think it'll make it a little bit clearer looking at both. So in other words, if -2 is a 0 of multiplicity 3, that means -2 appears 3 times. Although it's one solution, in the way that we factor, it's going to appear 3 times. So in other words, we would have x, so basically x equals -2, x equals -2, x equals -2. So that's happening 3 times. So that when you rewrite it, it becomes x plus 2 equals 0, x plus 2 equals 0, and then again, x plus 2 equals 0. But that just turns into factors. So if you look at the solution there, when we factored it, it became, or when we wrote it as a factor, excuse me, it's f of x is equal to a, that leading coefficient that we don't know yet, and it's going to be multiplied by x plus 2, but that expression or that binomial raised to the power of 3. So that's kind of reinforcing the whole degree 3 also. So if we evaluate that now for negative 1, so if we evaluate that, we're just going to substitute all of that in. So f of negative 1 in this case is 4. And when we plug in negative 1 for x, it becomes 1 raised to the power of 3. But that's just 1. So the leading coefficient in this case is 4. So the condition to have a function f defined by a polynomial of degree 3 that satisfies the given conditions of negative 2 is a 0 of multiplicity 3, and f of negative 1 equals 4, it's going to be this right here. F of x is equal to f times the cubing of x and 2 when added together, or what we're looking at here. And again, you could multiply it all out and you'll get that longer polynomial. 4x cubed plus 24x squared plus 48x plus 32. So we're going to stop here for today. Are there any questions? Any questions? I know there's an extra section in this in the packet or in the slides. I'm debating whether we should cover that or not. That I'll know better by Friday. But you have more than enough background to actually complete tonight's homework. Any questions? No. Thank you, Leah. Thank you, Mohammed. No. Thank you, Valentina. Well, I hope this class was better than yesterday's. Well, yesterday was kind of in vain, but not really. So, oh, there I am. You probably see me. I don't know what happened. I would rather not be seen. That's all right. But anyway, I hope you have a good day, and I will see you on Friday. Again, if you have any questions, just send me an email. I'll be virtually around for the remainder of the day, for the remainder of the week, and I'll see you soon. And the homework will be posted. See you later.